Hello, everyone, and welcome to the first expert session on NGR monitoring and compliance with CEC 2024. My name is Sonny Solanki, and I'm the Senior Technical Manager with 8 to 9 years of experience in resistance grounding and protection systems. And we are going to be looking at what the importance of NGR monitoring is and how we can make sure that we comply with CEC 2024, as well as the new features for our new Sigma 3C relay. So to start off, for system grounding, resistance grounding typically involves adding an impedance between the transformer neutral and ground to limit the ground fault current, and this limitation prevents the buildup of sufficient energy for arcing, thereby fostering a safer operational environment. So instead of the typical scenario where we have a solidly grounded connection from XO to ground, we instead place a neutral grounding resistor in an effort to limit any phase to ground fault by putting a resistor in series so that we can clamp the current level of that ground fault. And on the right, we have the IEEE standard green book. It indicates the reasons for limiting the current by resistance grounding may be one or more of the following. To reduce the burning and melting effects in faulted electrical equipment, such as switchgear, transformers, cables, and rotating machines. To reduce the mechanical stresses in circuits and apparatus carrying fault currents. To reduce electrical shock hazards to personnel caused by stray ground fault currents in the ground return path. And to reduce the arc blasts and hazards to personnel who may have accidentally caused or happen to be in close proximity to the ground fault. We also help to reduce the momentary line to voltage dip occasioned by the occurrence and clearing of a ground fault in comparison to what we see in other systems, and we secure control of transient overvoltages while at the same time avoiding the shutdown of a faulted circuit on the occurrence of the first ground fault. So mostly the main benefit is reducing the electrical and mechanical stresses that we would see in a solidly grounded system when we have high levels of fault current by reducing that fault current to a specific value that we dictate, typically 5 or 10 amps for low voltage systems. Now in NFPA 70E, which is a standard for electrical safety in the workplace, we also have an equivalent in the Canadian standard, which is the CSA Z462. Both of them closely mirror each other. And in Annex O.2.2, it says that design option decisions should facilitate the ability to eliminate hazards or reduce risk by doing the following: reducing the likelihood of exposure, reducing the magnitude or severity of exposure, and enabling achievement of an electrically safe work condition. Further to this, in Annex O.2.3, they list out 9 different incident energy reduction methods. Of the 9 listed, high resistance grounding is the only one reducing the likelihood of exposure, whereas all the other incident energy reduction methods are acting after the fact that the arc is already in the system and it's looking to trip the upstream protection once the arc has been detected. Whereas with high resistance grounding, we're placing that resistor at the neutral point to ground already in advance of any phase to ground fault. And then when a phase to ground fault occurs, it leaves insufficient fault energy and helps reduce the arc flash hazard level by clamping that current to a value of 10 amps or less. The only thing with high resistance grounding is that it doesn't affect the arc flash energy for line to line or line to line to line arcs, because the NGR at the source is not going to see any of the current that's circulating between 2 or 3 faulted phases. As a result, your instantaneous function of your breaker is likely to trip in the event of a phase-to-phase or a 3-phase failure. Now, in the National Electric Code in 250.36 for impedance grounded systems between 480 to 1000 volts, impedance grounded systems in which a grounding impedance device, typically a resistor, limits ground fault current shall be permitted for 3-phase AC systems between those 2 voltage levels if the following conditions are met. The conditions of maintenance and supervision ensure that only qualified persons service the installation. Ground detectors are installed on the system, and line to neutral loads are not served. So in this case, the National Electrical Code actually prohibits the distribution of the neutral. In addition to that, we noticed that for National Electric Code, they don't have a requirement to provide resistor monitoring. It's only about ground fault detection in this case. Now, the grounding impedance is selected to limit fault current to a value that is slightly greater than or equal to the capacitive charging current. The system is used where continuity of power is required. Therefore, a ground fault results in an alarm condition rather than in a tripping of a circuit breaker, and the alarm allows for safe and orderly shutdowns of a process for which a non-orderly shutdown could introduce additional or increased hazards. Now, when we compare this to the Canadian Electrical Code, we can see that we've had a lot of changes starting from 2018 to 2021 and then to 2024. 2018 is where they introduced impedance grounded system section in section 10 of grounding and bonding. And it indicates that in 10-302 that the integrity of an impedance grounded system shall be monitored and controlled as required by table 17. On the right, we have table 17, and we have 3 conditions which we need a monitor for. And the table gives you the conditions for which you need to initiate an automatic alarm or de-energize your system. On the left-hand side here, you have your impedance grounding system configurations. Now, with respect to the conditions, the first column is in relation to ground faults in the system. The second column is in relation to when we have a shorted NGR, where our system now becomes solidly grounded. And then the third column here is in relation to an open circuit system, where we now have an ungrounded system. On the left-hand side, the impedance grounding system configurations, we have stipulated a stipulation for line to neutral loads being served with a fourth wire being distributed throughout the system. And in this case, for each of the 3 conditions, it says alarm and de-energize the system immediately. At I-Gard, we recommend not to distribute the neutral in a resistance grounded system because it's considered dangerous, and it's also banned by NEC 250.36. The reason being is that when a ground fault does occur, the neutral voltage elevates, and it can definitely impact those single phase loads when a ground fault is present. Now, the area where a lot of consultants and end users are taking advantage is the second row, where it indicates line to neutral loads are not served, so the system's 3-phase 3-wire. The system's at 5 kV or less, and ground fault is limited to 10 amps or less. In this case, for the ground fault scenario, it says alarm and de-energize the system within the time rating of the impedance grounding device. But in this case, when we typically specify high resistance grounded systems, we typically go with a continuous rated resistor so that we only have to alarm the condition of ground fault without having to de-energize. Now in the third row, we have our low resistance grounding idea, where if your system is greater than 5 kV or ground fault is greater than 10 amps, it indicates to alarm and de-energize the system within the lesser of 48 hours or the time rating of the impedance grounding device. But typically, most consultants are typically tripping on first fault and using a 10-second or 60-second rated resistor. Now, when it comes to the short circuit scenario for both rows, it says to alarm and de-energize the system within 48 hours. And for the open circuit condition, we either alarm if we can still detect a ground fault in an ungrounded system, or we alarm and de-energize the system within 48 hours if we cannot. Now our new relay, the Sigma 3C, is fully compliant with table 17, including adding the 48-hour delay, and it can also detect a ground fault in an ungrounded system by picking up that neutral voltage elevation, and with the fact that we're not seeing any current at our CT due to the open circuit. Now, resistor monitoring, we have our Sigma 3C relay here. It combines ground fault protection and resistor path fault monitoring to safeguard systems from ground faults and open or short circuits in the neutral grounding resistor and its connecting conductor. So instead of just monitoring the NGR, we're actually monitoring the entire path between XO and ground in an effort to pick up any open or short circuit conditions throughout that entire path. That's why we switched to resistor path fault monitoring rather than just NGR monitoring. So this is designed for system ranging from 480 volts to 69 kV. It monitors resistance as low as 6 ohms and is compatible with HRG systems up to 5 kV and fault currents up to 10 amps, and for LRG systems where if you're at 5 kV and above and fault currents ranging from 10 amps to 1000 amps. Now, in the past and in the United States as well, we see that a lot of approaches taken are just using a ground fault relay with a CT connected at the neutral. But when we have an open circuit condition, that CT is not going to see anything, and you're also not going to know that your system has now become ungrounded. This can impact your protection schemes downstream that are using a line to ground reference, because now the ground reference is lost. And in addition to that, we also have our short circuit scenario where our system becomes solidly grounded and our CT can potentially be bypassed here. In this case, we won't know that the system is solidly grounded. The protection scheme downstream may not be set properly for a solidly grounded configuration, and we're no longer protecting the system from high levels of fault current, which could lead to arc flashes or arc blasts. So that's where, with our Sigma 3C monitor, we include a sensing resistor in parallel with the neutral grounding resistor. The sensing resistor gives us capability for getting a reference for the neutral voltage here and normalizing it between the R and G terminals back to the relay so that the relay can read what kind of voltage we're seeing at the neutral. We also have our CT connected for the current. And in addition to that, we're also using a high frequency AC injection, which is taking the path up through the neutral to the XO point and down through the NGR back to the relay. The reason why we're using a high frequency signal is because the windings of a transformer or generator are typically modeled as inductances. And because our inductance is XL equals 2 pi FL, with a high enough frequency, this inductance becomes a higher impedance than the NGR itself, such that majority of our signal will take the path down through the NGR and back to the relay. Now, our relay also has a DC-based superpositioning on this high-frequency signal to also do DC-based injection through the NGR. And that's an additional measure utilized to combat a lot of capacitance in the system. Now, when the competitor is using strictly a DC-only injection through this path, they see these inductances as short circuits, and they could have issues with YY connected PTs where the primary is grounded because their DC signal leaks out into the system and finds this alternative path to ground. These PTs here have a very high AC resistance, but their DC resistance is very low, such that this signal can get through and falsely claim that it's checked the NGR when it hasn't, or falsely indicate that the NGR is in a fault condition. So we've already discussed table 17, but I like to mention that typically row 2 is dictating for high resistance grounding, where your system voltage is less than 5 kV and fault current is less than or equal to 10 amps. And then row 3 is typically reserved for low resistance grounding if your system voltage is greater than 5 kV or fault current is greater than 10 amps. Now, if we have a short circuit scenario and we're injecting this high frequency signal while there is 0 volts and 0 amps at the neutral, what happens is if we get this full signal back because it bypasses the resistor and doesn't experience the voltage drop across the NGR, and the relay sees that the full signal has come back, then we can indicate a short circuit condition. In the case where our high frequency signal is moving around the circuit and down through the NGR, and suddenly an open circuit occurs, our relay starts a counter to see if that signal is going to come back, and if it doesn't come back, then we indicate an open circuit. We also have a measurement mode where when a certain amount of voltage and current is picked up by our sensing resistor and CT, we use that current and voltage to back calculate a resistance and compare that measured resistance to the actual resistance of the NGR. If it's beyond 150% or below 66%, we can indicate a fault condition. So this measurement mode is only active when the voltage and current is above 5% of the threshold. When it's below 5%, we're still injecting this high frequency and DC-based injection method. Now, the special features that are coming into play is that we are using a high frequency AC signal and a DC signal. So in injection mode, a 4 kilohertz high frequency AC signal is injected. And when the signal reaches the XO point of the transformer, most of the signal flows through the NGR path as discussed to properly monitor this entire path. And we also utilize a DC signal superimposed on the high frequency AC signal for additional stability and monitoring performance, especially for instances where there's a lot of capacitance in the system. In addition to that, there is an auto calibration feature which is going to be rolled out that allows the unit to auto calibrate once connected to the system to ensure system parameters are accounted for with respect to detection of open and short circuit conditions. And we're also performing CT monitoring, so the relay can detect if the current transformer is open or shorted, and it provides an alarm to alert users to any issues with the CT. This complies with the Australian Standard 2081-2023 Section 6.4, where it indicates that an open circuit or short circuit in the cabling to a current sensing transducer or the current sensing transducer itself shall result in the protection device initiating a trip of the circuit interrupting device within a time period not exceeding 5 seconds. This came about because there was quite a considerable amount of installations that were experiencing CT damage, and that CT damage didn't allow for the resistor monitoring to properly work and potentially cause nuisance alarms. So this capability for this relay allows it to provide the operator additional benefit in understanding that the CT itself has failed rather than going through all the troubleshooting process to find that out later. That is it for today's presentation. Let me know if you have any questions. I'll be opening up the question tab now. Let's see here. There's a chat. Questions. There we go. The Sigma 3C changes are interesting, but most of our customers buy the DSP DRM3 unit. What are the plans to have the DRM3 unit comply to Table 17, especially in regards to the 48-hour trip time? So we're in the process right now to upgrade the DSP system because we've been mostly focusing on the resistor monitoring aspect and also trying to comply with the latest code changes. The next system that will be upgraded will be the DSP system, where we will also include that 48-hour delay and make sure that it is code compliant to the latest code. In addition to that, we also have interposing relay that can be utilized, which can achieve the 48-hour delay. So that's what we've been doing in the interim to satisfy the 48-hour requirement for the trip time. Is the NN connection point shown the XO of the transformer? So basically, when you have a neutral grounding resistor and our sensing resistor has to connect to that XO point, if it doesn't connect to the XO point and you jumper between N and NN and you just lead out one cable to the XO point, then you're reducing the monitoring capability from having it monitor the entire path to just up to the point where you've jumpered between N and NN. So the recommendation from I-Gard is to utilize 2 wires and connect both wires to the XO point. And we also provide 2 terminals within our NGR, one for N and one for NN. That way the sensing resistor gets its own connection and the NGR gets its own connection. The session is being recorded by Andrea and you will be able to have it. And I believe we're providing certificates for PDH as she's already answered that. So let's go to Faba Thomas. Where should the NGR monitoring relay ideally be located in relation to the transformer? Some transformer manufacturers have this installed in their transformer cabinets, which are enclosing the other controls that they have. Also, we can provide a NEMA 4X box with a heater to be placed at the transformer. If the transformer is close to your electrical room, then you can also put a NEMA 1 box inside the electrical room with the relay and then connect the wires back out to the NGR, which would be located either next to the transformer or on top of the transformer. Do utilities typically accept NGRs if they require the neutral for metering? If you look at section 6-412 of the Canadian Electrical Code, it gives you advice on how to pull a neutral connection for metering. So I suggest you to look at that for when you're doing high resistance grounding and you need a neutral for metering. Simone, do you have a testing device to simulate the Sigma relay testing and functionality? We don't typically provide a testing device, but in some commissioning and testing applications, which we have been involved in, is we typically send out a test resistor, and the test resistor is fused, and we put a resistive fault on one of the phases to ground to ensure that we can see the ground fault. And the ground fault is a combination of being picked up by not only the CT, but also by the neutral voltage elevation. So our sensing resistor has to see voltage increase as well. If you just inject current through the CT, you're actually going to get an NGR fault because the CT is seeing current, but it's not seeing the neutral voltage elevation. So it's going to think something's wrong with the NGR. So it's a combination of both neutral voltage and neutral current, which will qualify a ground fault in this case. What is the ambient temperature range for the CT and sensing resistor? We can go for about -40 to +60. I think the CT Our standard CT is from 0 to plus 60, but we also have another CT called the TR6EC, which goes from minus 40 to plus 60. The sensing resistor circuitry is potted so that it's protected from the external conditions and has that temperature extension range from minus 40 to plus 60. Does the Sigma 3 have a software interface? The Sigma 3C actually connects to a touchscreen display module, and everything is set on the touchscreen display as well as the Sigma 3 dip switch settings. So there's some hardware settings, which are the dip switch settings, and then the rest of the software settings are usually handled on the touchscreen display. We don't have like a software interface or a cable connection to configure the relay. That's usually just done on the touchscreen display. So this is Mahesh. What needs to be considered when incorporating DSP of NGRs to existing service entrance boards where there's no space for CTs? If there's no space for CTs, maybe you would not consider a DSP system, but rather a Sigma 3, because the retrofitting of CTs when there's no space means that the DSP system is like basically only doing resistor monitoring. So the preference is that for existing service entrance boards, you probably go with the Sigma 3C because it's more plug and play. So we have a sleuth panel, which has the resistor monitoring, and the terminal blocks. And basically, when you get that unit, it's wall mountable. You place it on the wall. You have 120 volts AC connection, and then you just put your two neutral connections in your ground and wire your dry contacts up, and then the system is good to go without interfering with, the service entrance board and the CTs. And then with respect to fault locating, you can just use the pulsing feature with a manual clamp-on ammeter, like a Rogowski coil, to locate the position of the fault on this existing board. Can you explain whether you simulate all the fault conditions in commissioning? So for the open circuit and short circuit condition, we conduct these tests while the system is offline because it's dangerous to do that while the system's online. So with the open circuit, we basically just lift off the N connection from the XO point and see if the relay is picking it up. With respect to the short circuit connection, we just jumper between neutral and ground within the NGR while the system's offline and ensure that the DRM3 module is picking it up, or the Sigma 3C. And then with respect to ground fault, it's very difficult to simulate unless you have a test resistor, which can also allow for that neutral voltage to elevate. And that test is typically done in the online instance. Is introducing the ground fault on the energized system as you described mandatory to validate the installation? I would say that it's dependent on what the specification specifies for what you should be validating. But in most cases, what we want to see is that the CT is able to pick up the level of current that we pass through it. And in some cases, most customers will just push a wire through the CT and at least bring the unit to an NGR fault by pushing 2 or 3 amps through the CT. And as long as the screen is also picking up the same value of current flowing through the NGR, then it validates that the CT is working properly. And then from there, our sensing resistor will be picking up neutral voltage in like a typical ground fault scenario, and then the relay should be operating because the CT has already been validated. What cybersecurity certification do you offer? I'm not sure, to be honest. This is the first time I'm hearing this question. We have external communication connections on the touchscreen display module, and that's available via Modbus TCP/IP. And the operator just has to configure their user interface to accept the addresses for what they want to read with respect to NGR fault, ground fault, and system status. During a ground fault, how is the fault current shared between transformer NGR and system capacitance? So when a ground fault occurs, IF is a product of the let-through current of the NGR and the system charging current, which comes from capacitance that exists between the conductors and ground. Typically, for low voltage systems, 5 amps or 10 amps allows majority of the fault current IF to go through the resistor to dissipate that electrical energy into thermal energy. Because we know that for low voltage systems, the system capacitance charging current is very low, like maybe 1 amp or less. And therefore, that 5 amp blanket basically more than covers the system charging current. The idea is that we want the let-through current of the resistor equal to or greater than the system charging current, so that the major component of IF actually goes through the let-through current of the resistor. And then once it goes through the resistor, it goes to the XO point, up through the faulted phase, and back to the point of fault, because current likes to close the loop in that scenario. And the capacitance of the faulted phase is shorted, and the unfaulted phase capacitance is what allows the voltage to elevate to maintain the line-to-line voltage and allow you to continue operating. Why is the resistance measurement window to declare a resistor fault 60% to 150%? So it's 66% to 150% because that is the window that we deemed to be appropriate. I think it comes from some discussions in groups that were in relation to M421, as well as some discussions that we were having with respect to measurement tolerances of the CT of the sensing resistor. So 60% to 150% is what we selected. Some other manufacturers also have even broader windows of 10% to 200%. And our relay also has a dip switch setting, which you can change from 66% to 150% to another value of 66% to 300% if needed. Because most people may be more inclined for picking up the open circuit scenario than the short circuit. Do you support IEC 61850 protocol? Our Sigma 3C relay does not have that, but we typically buy a MOXA converter to convert the Modbus TCP over to the IEC 61850 protocol when it's called for. And that can be available and quoted as long as it's specified that you want this IEC 61850 protocol. Okay, I think I've gone through all the questions. If there's any other questions, feel free to reach out to my email. My email is here. And stay tuned for our next sessions where we will be discussing even more different topics. And we also have our 1 p.m. session as well, which will be on this same presentation. Thank you all for attending, and we appreciate your continued support. Thanks. Take care.